Good day, welcome to the second video on chapter 1.6 Planes. We will be doing lots of proofs in this video. Now recall that we defined a plane to be the set of points of the form r plus s p minus r plus t q minus r, where s and t are real numbers. Remember, vector p minus r and vector q minus r are not scalar multiples of each other. So p, q and r are 3D vectors. Now planes are very special objects. Now, a plane is a subset of R3, and they have some really nice properties as demonstrated by the theorems. All right? Please remember, short proofs you should be able to do, and long proofs you must understand, and we will most likely turn them into comprehension questions. All right, so first theorem. The first theorem goes as follows. Let L be a line in R3, and P a plane in R3. If line L intersects P in more than one point, then the line is contained in P. Or mathematically we say set L is a subset of set P. So L is a line and P is a plane. The proof, we need to first say, alright, have a setup. So P is a plane, so P is of the form R plus S, P minus R plus T, Q minus R, where S and T are real numbers. And P, Q and R are three vectors not lying on the same line. So say line L intersects P in 2 points, and we label the 2 points A and B. So the first question is, why is line L of the form TA plus 1 minus TB, where T is a real number? So this is a comprehension question, so let's quickly answer it. All right. So firstly, A is sitting in L intersect P because the line and the plane intersect in point. One of the points is A. Also, because A is sitting in A intersect P, so A must be an element of the line. Because if it's sitting both the line and the plane, it must be sitting on the line. All right? Likewise, B is sitting in the line intersect the plane, so B is sitting in the line. All right? Now, since A and B are distinct points, we know by theorem 1.4.16, it is true. All right? You can say it in words, i.e. unique line given two distinct points. So if you forgot the name of the theorem, you can say that there's a unique line that passes through two distinct points. So the next question is, why does there exist an S0 and a T0, real numbers, such that A is of the form R plus S0, P minus R plus T0, Q minus R? All right. Well, again, A is sitting in the line, intersect the plane. So now A is sitting in the plane. All right. And so to be sitting in the plane, it must be of this form for some scalars S0, T0. So you can just say, then by definition of plane P. The next question, why does there exist scalars S1 and T1 such that vector B is of the form R plus S1 P minus R plus T1 Q minus R? Similar reason. P is one of the points sitting both on the line and the plane. So vector B is sitting on the plane. And then we can say, then by definition of plane P. So there are scalars S1 and T1 that makes this true. All right. Now the next question is, take any point on line L. So it must be a 3D vector. We label it X. The question says, show that vector X is sitting in P. All right. So by A, X is of the form TA plus 1 minus TB for some T element of real by A. And now, let's scroll back to B and C. So in B, we know that A is of this beautiful form. And by C, we know that B is of this beautiful form. So let's capitalize on that result and let's fill it in. So A is of the form R plus. Remember the scalars that we get is S0. So it's S0 P minus R plus T1 Q minus R. And in B, we get that vector B is of the form R plus S1 P minus R plus T1 Q minus R. Remember to put lines above R, P, and Q because they are vectors. Now, if you look closely, if you look at, there's a TR term and there's a 1 minus TR term. If you add it and you simplify it, this becomes R. If you look here, you can take out a common factor of P minus R. What remains is TS naught. If you take out a common factor of P minus R, what remains is 1 minus T S1 P minus R. Likewise, if you take out a common factor of Q minus R, you get T times T1. And here you get 1 minus T T1 and then Q minus R. So a little bit of algebra. So you can see it is of the form R plus alpha P minus R plus beta Q minus R, where alpha is T times S naught plus 1 minus T S1 and beta is equal to T times T1 plus 1 minus T times T1. Alright, and now it is of the form R plus a scalar P minus R plus a scalar Q minus R. And remember, when we did the setup, vector P is of the form R plus scalar P minus R plus scalar Q minus R. So we have shown that vector X is of this form. So by definition of P, X is a vector of that form. So X is sitting in set P, a plane. All right. And now the final question is, why does this mean that the line is a subset of the plane or that the line is contained in the plane? All right. Explain it in one clear sentence. All right. So let's do it. So by D, we showed for any X in L that it implies that X is sitting in P. So let's make it a comma. So the result follows. So the result follows. So in set theory, if you want to show that set A is a subset of set B, then you've got to show every object in set A is an object that lives in set B. All right, so now we know that if a line cuts a plane in more than one point, the line is contained in the plane. All right, another theorem. If line 1 and line 2 are planes in space that intersect in exactly one point, then there is exactly one plane P that contains both lines. So do try out this proof yourself. It is exercise 1.6 number 3. All right, but let's quickly do an exercise to see this in action. So let line 1 be the set of points of the form 1, 2 minus 2t, 2t minus 1, where t is a real number. If you have a different line, you've got to use a different parameter. So let's say line 2 is a set of points of the form 2s minus 3, 3 minus s naught, where s is a real number. So I'm going to leave it for you to show that the two lines intersect and they intersect in a unique point. So that calculation might take a page. All right. Now another question then is, why does a unique plane exist containing both line 1 and line 2? All right. And now we can explain this beautifully. All right. We can say by A, you will show that there is an unique point on both lines. So by this theorem that I just mentioned, so by theorem 1.6.7, it now follows. So the theorem is quite powerful. Using the theorem, we can now prove there's a unique plane containing both of the lines. So the theorem says that if you have two lines and they intersect in one point, that's the condition. If that condition is true, then it follows that there's a unique plane containing both lines. That's theorem 1.6.7. And now, just to finish this question, let's try to find an equation for this plane. All right. So it's good to draw a picture. So if we draw a picture, we can say, okay, that's line 1, that's line 2. They intersect. Let's call this point A. This point A has coordinates 1, 1, 0. And I'm going to leave it for you to see that point P, which is 1, 0, 1, is sitting on line 1. And this point U is the point 1, 0, 1, and point U is the point -1, 2, 0. That is sitting on line 2. All right? And I'm going to ask you to verify, why is A, P, and U not on the same line? I'm going to leave it for you to think about. And now we can say an equation for this unique plane is, so A must be sitting on the plane, P must be sitting on the plane, U must be sitting on the plane, because the plane contains both line 1 and line 2. So we can now say that the plane is of the form. There are many forms, but I'm going to take the form point plus. Then we got to take a scalar. So let's say S, P minus A. I'm going to take another scalar, T, U minus A, where S and T are real numbers. And if you fill in the vector A, the vector P, and the vector Q, then you're going to end up getting A, which is 1, 1, 0, plus S. P minus A works out to be the vector 0, minus 1, 1, 0, minus 1, 1, plus T times U minus A. Double check my calculation, is the vector -2, 1, 0. And there you have an equation for this plane P, which is unique. Nice exercise. There are lots of exercises like this in the textbook. Alrighty, another theorem, as promised. So if you have 3 distinct points, P, Q, and R, and they do not lie on the same line, then again there's a unique plane in R3 that contains all 3 points. So I'm not going to do that proof in this video, so please see pages 44 and 45 in the textbook. But I'm going to do the next theorem. The next theorem says that consider lines L1, which is of the form Q plus T, P minus Q, where T is a real number, and line 2 is of the form B plus T, A minus B, where T is a real number. 2 lines in R3, so that the lines are different. Then there are 2 parts to the theorem. The first part is that if the lines are parallel, then there's exactly one plane containing both lines. And part 2 of this theorem says that if the lines do not intersect, and there is a plane so that line 1 and line 2 are contained in the plane, then the lines are parallel. Now, number 2 is quite a hard proof. A special case of the proof of number 2 is exercise 1.6 number 5. So if you feel adventurous, you can give that a go. But let's finish off this video by looking at number 1. So let's start with number 1, which says that if we have 2 lines, and they are parallel, and they are distinct lines, if the 2 lines are parallel, then there's exactly one plane containing both line 1 and line 2. So this is telling us that the lines are distinct, that line 1 is not line 2. All right. So the proof is again a comprehension question, so let's do the calculation. So the first question is, why is A minus B equal to alpha P minus Q for some scalar alpha? All right. Now let's go back. Line 1 is of this form. So you can see the vector in front of the parameter is P minus Q. The vector in front of this parameter is A minus B. So remember, what does it mean for lines to be parallel? If you've forgotten, pause this video, go to your textbook, have a look at what does it mean for lines to be parallel. All right? So because the lines are parallel, we can say that A minus B is equal to alpha times P minus Q. So your reason is simply because it is given that line 1 is parallel to line L2. All right, so that was short and sweet. The next question. Why is P, Q, and B not on the same line? All right, so the question is, why is P, Q, and B not on the same line? All right, so first of all, by theorem, so have a look at theorem 1.4.19. So by theorem 1.19, if parallel, so have a look, it tells you something cool about parallel lines. So if parallel lines intersect, they are the same. So by theorem 4. If parallel lines intersect in our model, if parallel lines intersect, they are the same. But we know that the lines are not parallel, all right? So, since L1 is not equal to L2, we get that the lines are not the same, all right? So we get that since, remember, P is sitting on line 1, Q is sitting on line 1, and B is sitting on line 2, we see that they cannot be all on the same line. So do make sure that you're comfortable with this logic. All right, the next question. Take the plane P of the form Q plus SP minus Q plus TB minus Q, where S and T are real numbers. So this is a set. So the question is this a plane? Why and why not? All right? And the answer is, by B, P minus Q is not equal to alpha B minus Q, since P, Q, and B not on the same line. Hence, by definition, this is a plane. So again, you need to know planes are sets of the form vector plus scalar times a vector plus a scalar times another vector, but the two vectors in front of the scalar should not be scalar multiples of one another. All right, now part D is, why is line 1 contained in P and why is line 2 contained in P? All right, and the answer is very simple. So first, point A and point B, point A and point B is sitting on line 2. Well, let me rephrase. So this is a plane. So if you look at the equation, you can see that in this plane, so for example, you can see S is equal to T is equal to naught. So you can see Q is sitting in P. And where is point Q sitting? Point Q is sitting on line 1. And so Q is sitting on line 1. And Q is sitting on line 1. So Q is sitting on both line 1 and the plane. All right. Now, if you make S equal to 1 and T equal to naught, then you get that P is sitting in the plane and P is sitting in line 1. So P is sitting on both line 1 and the plane. All right. Now I'm going to leave it for you. Similarly, show that line 2 is a subset of P. All right. Now, what have I done here? I've shown that point Q and point P is sitting on both line 1 and plane P. And now remember that we have a theorem. We have a theorem that says that if a line pierces a plane in more than one point, then the line must be contained in it. All right? So from this we can say, by theorem 1.4 1.6.6. So by theorem 1.6.6, it follows that line 1 is a subset of the plane. All right? If you've forgotten the name of the theorem, just simply say, I have proven that the line and the plane intersect in at least two different points, point P and point Q. And because the line pierces the plane P, intersects the plane P in more than one point, it follows that the line is a subset of plane P. All right, so the plane contains line 1. Similarly, you can show that line 2 is a subset of line P. All right, and so what we have done is we have proven the existence. So this proves the existence of such a plane. So we know that there is a plane that contains both these parallel lines. All right, so we have shown from part A to part D that there is a plane containing both lines. All right, this is deep stuff, guys, so do think about it. If you're unsure, please ask any of the lecturers in the 1 to 4 teaching team. All right, now we want to prove uniqueness. So existence does not imply uniqueness. All right, so we need to prove uniqueness. All right, so we need to prove that it is unique. All right, so we need to prove uniqueness. All right, now we can use our previous theorem. So let's see which theorems might be useful. We're proving 1.6.10, so we can't use it. So 1.6.9, maybe. We have 1.6, theorem 1.6.7, which we started off. Remember, we started off by showing that if the two lines in space intersect in exactly one point, then there's exactly one plane that contains both. And there's exactly one plane that contains both lines. All right? But now, here we have lines that are parallel and don't intersect. All right? So, but the question is, why is there a plane containing line 1 and line 2 unique? All right? So, the lines do not intersect, and we want to establish uniqueness. All right? So the planes don't intersect, and we want to establish uniqueness. All right? So this is something that is not immediately obvious, so you need to think carefully about this. All right? So I'm going to start it, and then I'm going to leave it for you to finish. All right? So what you do is, we know that plane P has this property. Plane P has this property. So take another plane with this property. Call it Q. So line 1 sits in Q and line 2 sits in Q. All right? And I'm going to leave it for you. If you get stuck, look at an exercise in the textbook. Have a look at exercise 1.6 4b. So have a look at exercise 1.4 4b, and somehow you can deduce. So I'm outlining the logic. You can deduce that P equal to Q, and therefore you have uniqueness. So this is something new that you might not have seen in 114. So to prove, we first have to show that the plane P exists, and this is what we've done from A to D. Once we've done that, then we say that, okay, let's say we have another plane with this property Q. It could be the same one, it could be a different one. So then we say we have plane Q, and plane Q contains line 1 and line 2, and then a little bit of mathematical logic happens, and then you can deduce that P is equal to Q. So it means that if I have a plane P with this property and you have a plane Q with this property, it must be the same plane. So therefore you have uniqueness. I hope you enjoyed this video. Do listen to it again and have a lovely day. Bye.